Something beneath Yellowstone has started to change again. Scientists monitoring the park have detected subtle shifts in the ground at one of its most unstable geothermal regions. The place where these changes are appearing is not random. They are happening inside Norris Geyser Basin, a place geologists have watched closely for decades because it behaves differently from almost anywhere else in Yellowstone. Visitors walking through the basin today probably would not notice anything unusual. Steam rises from vents in the ground just as it always has. Pools bubble quietly beneath wooden boardwalks. Tourists stop to photograph colorful hot springs and drifting plumes of vapor. From the surface, Norris Basin appears almost timeless. But instruments buried across the basin are detecting a different story. Tiny shifts in the ground, small earthquake signals, subtle changes in the movement of hot water and steam beneath the surface. Each signal on its own might not mean much, but when scientists see these signals appearing together in a place like Norris Basin, they know something beneath the ground may be slowly rearranging itself. Researchers from the Yellowstone Volcano Observatory, a scientific collaboration led by the U.S. Geological Survey, monitor Yellowstone continuously using a network of seismometers, GPS stations, satellite measurements, and gas sensors capable of detecting incredibly small changes beneath the surface. Some of these instruments can measure ground movement of only a few millimeters. Others can detect earthquakes far too small for humans to feel. Together, these tools allow scientists to watch Yellowstone's underground systems in ways that were impossible only a few decades ago. By combining these measurements, researchers can see how pressure moves through the crust, how fluids circulate beneath the park, and how the landscape slowly shifts over time. And Norris Basin is one of the places they watch most carefully. The reason is simple. Norris Basin has a reputation among geologists. It is the hottest geothermal area in Yellowstone and one of the most dynamic hydrothermal environments anywhere on Earth. Underground temperatures here have been measured above 450 degrees Fahrenheit. Under pressure, water at those temperatures can remain liquid even though it is far hotter than its normal boiling point at the surface. When that superheated water suddenly finds a pathway upward through fractures in the rock, the pressure release can be explosive. Sometimes it powers geysers. Sometimes it reshapes the landscape. And occasionally, it produces sudden changes that surprise scientists. One of the most famous features in Norris Basin is Steamboat Geyser, the tallest active geyser on Earth. When Steamboat erupts, water can blast more than 300 feet into the air, roughly the height of a 30-story building. But what makes Steamboat remarkable is not just its height, it is its unpredictability. For years, the geyser may remain mostly quiet, then suddenly can enter a period of intense activity, erupting repeatedly over the course of months or even years. Between 2018 and 2019, Steamboat erupted more frequently than at any point in recorded history. Then, activity slowed again. To scientists, this irregular behavior reveals something important. The underground plumbing system beneath Norris Basin is constantly evolving. To understand why Norris Basin behaves this way, it helps to imagine what the ground beneath Yellowstone actually looks like. If you could somehow cut through the earth beneath your feet and look underground, you would not see a solid mass of rock stretching downward. Instead, you would see a tangled maze of fractures filled with boiling water, steam pockets, and mineral deposits slowly forming along the walls of those cracks. Some pathways carry hot water upward toward geysers and hot springs. Others trap superheated water underground until pressure builds high enough to force it toward the surface. Over time, minerals dissolved in hot water slowly deposit along the walls of these fractures, sealing some pathways closed. Meanwhile, pressure building elsewhere forces new fractures open. The result is a constantly evolving network of underground plumbing. When that plumbing changes, the surface of Norris Basin changes with it. Geysers may suddenly stop erupting. New vents may appear where there were none before. Thermal pools may form where solid ground once existed. Scientists have documented several periods when the entire basin appeared to reorganize itself, with multiple geothermal features changing behavior within a relatively short span of time. These shifts can occur gradually over months or years, but sometimes they appear surprisingly quickly. Another reason Norris Basin behaves differently from other geothermal areas in Yellowstone is its unusual chemistry. Many geothermal basins in the park contain mostly alkaline waters, but parts of Norris Basin are highly acidic. This tells scientists something important about what is happening beneath the surface. In certain areas of the basin, volcanic gases rising from deep underground interact with groundwater circulating through the rock. One of the most important gases involved in this process is hydrogen sulfide. When hydrogen sulfide mixes with oxygen near the surface, chemical reactions can produce sulfuric acid. This acid alters the surrounding rock and creates the distinctive acidic thermal features that make Norris Basin unique. Acidic waters can dissolve minerals in the rock, gradually widening fractures and creating new pathways for fluids to flow. This process further contributes to the constantly evolving underground plumbing network beneath the basin. Because of this chemistry, Norris Basin contains some of the most extreme geothermal environments in Yellowstone. Water temperatures are extremely high, and the chemical conditions can be harsh enough to dissolve rock over time. Yet even in these extreme environments, life exists. Microorganisms known as thermophiles thrive in the hot waters of Yellowstone. These microbes can survive in temperatures that would destroy most other forms of life. Many of the vivid colors seen in Yellowstone's thermal pools are actually created by communities of these microorganisms. The oranges, yellows, greens, and browns surrounding many hot springs are formed by microbial mats growing along the edges of the pools. Each color represents different species adapted to specific temperature ranges. Scientists study these organisms closely because they provide clues about how life can survive in extreme environments. Some researchers even study Yellowstone's microbes to better understand how life might exist elsewhere in the universe. If organisms can survive in boiling acidic water on Earth, it raises the possibility that life could exist in similarly extreme environments on other planets or moons. Another reason Norris Basin receives so much scientific attention is that the ground here has experienced episodes of subtle movement over time. Instruments measuring ground deformation across Yellowstone have occasionally detected small periods of uplift and subsidence in different parts of the park. These changes usually occur slowly and are often related to shifts in underground hydrothermal fluids. When hot water moves through fractures beneath the surface, it can build pressure within the rock layers above it. That pressure can cause the ground to rise slightly. Later, as fluids move away or pressure decreases, the ground may settle again. These small changes in elevation may only amount to a few centimeters, but they provide valuable clues about how Yellowstone's hydrothermal system is evolving. Scientists combine ground deformation measurements with earthquake monitoring and gas measurements to better understand how pressure moves through the system. In most cases, the changes they observe simply reflect the natural evolution of Yellowstone's geothermal plumbing. At this point in the story, it is worth mentioning something important. If you enjoy exploring the geology shaping our planet and learning how scientists monitor powerful natural systems like Yellowstone, consider subscribing to Strata Uncovered. The goal of this channel is to break down complex geological processes and explain the science behind them in a way that is both fascinating and easy to understand. Back beneath Norris Basin, the powerful geothermal engine driving Yellowstone continues to move. Water circulates downward through fractures in the crust. Heat rises upward from hot rock deep underground. Steam builds pressure inside hidden chambers. Minerals dissolve in hot water and redeposit along underground pathways. Slowly and constantly, the entire system rearranges itself. One of the most dramatic processes associated with geothermal systems, like Norris Basin, is something known as a hydrothermal explosion. Unlike volcanic eruptions, hydrothermal explosions do not involve magma reaching the surface. Instead, they occur when pressurized water trapped underground suddenly flashes into steam. When water turns into steam, it expands dramatically, sometimes more than 1,600 times its original volume. If that transformation happens suddenly beneath the ground, the pressure can blast rock, mud, and debris into the air. Hydrothermal explosions have created large craters throughout Yellowstone. One of the largest examples is the crater at Mary Bay Explosion Crater, believed to have formed roughly 13,000 years ago. The explosion that created that crater scattered debris across a large portion of the surrounding landscape. Events like this are extremely rare, but they demonstrate the immense energy stored within Yellowstone's hydrothermal systems. Earthquakes provide another important clue about what is happening beneath the park. Yellowstone experiences thousands of small earthquakes each year. Most are far too small for people to feel. In hydrothermal areas like Norris Basin, these earthquakes often occur when hot water moves through fractures underground. As fluids force their way through cracks in the rock, they can lubricate faults and trigger small seismic events. Scientists refer to these clusters of earthquakes as swarms. Hydrothermal systems like the one beneath Norris Basin are not unique to Yellowstone. Similar geothermal landscapes exist in volcanic regions around the world. In countries like Iceland and New Zealand, geothermal fields display many of the same processes seen in Yellowstone, but Yellowstone's hydrothermal system is one of the largest and most powerful on Earth. Walking through Norris Basin today, visitors see a landscape that almost looks alien. White mineral deposits coat the ground. Pools shimmer in bright colors created by heat-loving microorganisms. Steam drifts across the landscape as hot water escapes from underground vents. Yet beneath that surreal surface lies a constantly moving system powered by heat deep within the earth. Water circulates downward, heat rises upward, steam builds pressure, minerals dissolve and redeposit along underground pathways. Over time, the system rearranges itself again and again. New fractures open while others seal closed. Geysers activate and fall silent. Pools expand, shrink, or change color as microbial communities adapt to shifting conditions. Yellowstone may appear timeless from the surface. The same geysers erupt year after year. Steam drifts across the landscape just as it has for centuries. But deep underground, the system is always moving. Heat rises from ancient magma reservoirs. Water circulates through fractured rock. Pressure builds, shifts, and eventually releases again. And places like Norris Basin are where those hidden forces come closest to the surface. Even when Yellowstone appears quiet, the powerful geological engine beneath it is still very much alive.